What's going on, everybody? In this video I'm going to talk about some other types of polynomials that you can solve that are of higher degree. So we have been focusing on quadratic equations as the highest degree so far. So sometimes you're going to have equations that have terms like x cubed and x to the fourth in those. So there are special types of equations in which we can use factoring to solve for them easily. So in this video I'm going to give you a few examples of that. And later on down the line I'll be talking about polynomials a bit more in depth. But for these are some special cases. So if you can see equations that have these kind of forms, then you can use these methods. So the first example is I have 5x to the fourth minus 12x cubed is equal to 0. So in this case, I can see that I have x's in both of the terms. But not only that, I have an x to the fourth power and an x to the third power. So what I can do is I can take out as many x's in each of the terms as I possibly can. And that's going to be an x cubed. So what I can do is I can rewrite this as x cubed times 5x minus 12. And I've factored out the x cubed. So now I have two different factors, the x cubed and the 5x minus 12. So similar to how we solve the quadratic equation by factoring, we set each of the factor pairs equal to 0. So this is exactly what we're going to do here. So I have x cubed is equal to 0, and then I have 5x minus 12 is equal to 0. So the first one is easy. You just take a cube root of both sides, and the cube root of 0 is 0, so I have x is equal to 0 for the first answer. And this makes sense because if you plug 0 back into the equation, both of the terms are going to cancel, and you're just going to end up with 0 again. And as for the second one, it's just a linear equation, so I'm just going to add 12 to both sides. I get 5x is equal to 12, divide by 5, and I have x is equal to 12 over 5. So in the next example, let's see, I have 4x cubed minus 6x squared is equal to 0. So again, I notice that I have x's in both of these terms, and I also have multiples of 2 in each of the terms. So what I can do is I can factor out a 2 and 2x's, because the lowest degree exponent is x squared, and all of the terms have x's, so I can take out at least an x squared out of both of these terms. So what I'm left with when I do that is a 2x minus 3, and set that equal to 0. And if I FOIL this back out, I'm going to have the original polynomial again. So you set each of the factor pairs equal to 0. So I'll have 2x squared is equal to 0, and I'll have 2x minus 3 is equal to 0. So first, I'm going to divide both sides by 2. So I have x squared is equal to 0, and then I take the square root of both sides to have x is equal to 0 as my first answer. And again, this makes sense because if you plug in 0 for the x's, then both the terms cancel, and you'll just have 0 equals 0. And for the next equation, it's just a linear equation. So I have 2x is equal to 3, and then divide both sides by 2, and you get x is equal to 3 over 2 for the second answer. So another example here, let's say that I have the equation x to the fourth minus 6x squared. Oops. So for the next example, let's say that I have x to the fourth minus 5x squared plus 6 is equal to 0. So notice, what type of equation do we have? We have one that is in this form, ax squared plus bx plus c. But it's not quite, because we don't have second degree exponents. But what I do know is that it is in the form of this because we have evenly reducing powers across each of the terms, and there's 3 of them, and we have a constant term. So what I can do is I can make the substitution that u is equal to x squared. And so when I do that substitution, what I end up with is a u squared minus a 5 times u plus 6 is equal to 0. And then now we can solve this like we regularly would for a quadratic. So I'm going to try to factor this. And so if I have u is equal to 0, the factors of 6 that I'm going to use are negative 3 and negative 2 because those add together to get negative 5. So I have a minus 3 and a minus 2 here. And so you solve it regularly. So I have u minus 3 is equal to 0, and I have u minus 2 is equal to 0. So I get u is equal to 3 and u is equal to 2. But we're not done yet because we have to make the substitution back. So this really means that x squared is equal to 3. And it means that x squared is equal to 2. And so to solve this, you just take the square root of both sides of each equation. You have x is equal to the positive and negative square root of 3, and x is equal to plus or minus square root of 2. Okay, so last example for this, and let's say that I have 9x to the fourth power plus 27x cubed minus 4x squared minus 12x is equal to 0. So the first thing that I notice is that I have an x in each of these terms, so I can factor it out. And it looks like that I have common multiples among the terms, but in reality I actually don't, because 9 is not divisible by 4, 4 is not divisible by 3, so it'd be kind of a pain to take out some factors in terms of the coefficients. But I can take out an x. So what I'm going to do is I have x times 9x cubed plus 27x squared minus 4x minus 12 is equal to 0. And so for the term inside the parentheses, I'm going to be using factoring by grouping. So basically, you take the first two terms and find common factors within that group and factor it out. And then you do the same thing for the second two terms. So when I execute that, it's going to look like this. So in the first two terms, I have a 9x squared that's common, so I can take it out. And then what I'm left with is an x plus 3. And then in the second term, I have a 4 that's common, so I'm going to take it out. And then what I'm left with is another x plus 3. And keep in mind, this is a plus because if I multiply negative 4 back out, I'm going to get this minus 12 that we need. So this is the correct factorization. And then again, I have a common factor of x plus 3 in both of the new terms I just made, so I can take that out in the parentheses also. So I have an x plus 3 times a 9x squared minus 4. So 9x squared minus 4 has the form of a squared minus b squared, which is a difference of 2 squared, and that factors as a conjugate. So you have a plus b times a minus b here. So what I have is I have x times x plus 3 times 3x minus 2 times 3x plus 2. Because in this case, a is equal to 3x, so a squared is equal to 9x squared, and b is equal to 2, because b squared is equal to 4. So let me just erase this real quick and set this equal to 0. So now that this is completely factored, to ensure that 0 is returned, at least one of these terms needs to come out to 0. So the way that you find all the solutions is by setting each of the terms equal to 0. So I have x is equal to 0. That's already solved, so I can just circle it as an answer. I have x plus 3 is equal to 0. I have 3x minus 2 is equal to 0. And 3x plus 2 is equal to 0. So in this equation, all I need to do is add 3 to both sides, and I get x is equal to negative 3. Subtract 3 from both sides, excuse me. And for this guy, it's a linear equation. So I add 2 to both sides, then divide by 3. So I have x is equal to 2/3. And then for this one, I subtract 2 and then divide by 3. So I have x is equal to minus 2/3. And that's how you find the solutions for a problem like this. So I wouldn't get intimidated just yet if you see equations that have higher degrees earlier in your class, because it's likely that you're going to be able to factor something out and then solve the rest of the equation with a method that you've already learned before. So we're just adding an extra step here, thinking outside the box a little bit. But these are some techniques to help you solve some special kinds of higher degree polynomials. So I hope this video was helpful. You found something out of it, learned something. Stay tuned for the next one. Take care, guys.